This screencast is going to look at one of the features of molecules when they take on a three-dimensional shape, and we're going to focus on bond angles. There are a couple of different factors in a molecule that can affect the bond angle, and you identify the bond angle by looking at the electron domain geometry. Okay, so if our electron domain is linear, we have a molecule with two things bonded and two things bonded and no lone pairs. So that has two bond domains, and that is a linear geometry. In a linear geometry, the bond angle is quite simple to figure out. It is 180 degrees. There are going to be no real factors that are going to change the bond angle. You can have double bonds, you could have a triple bond, and a single bond. And the overall factor is going to be that both of the bond domains are going to have the same effect. They're going to push and repel each other with the same net force, and the bond angle is 180 degrees. There are two reasons that you can have a bond angle that's not what you would expect. The first is when you have lone pairs and they repel each other. Now remember, lone pairs are made up of electrons that are unshared. And when they push on each other, they have a pretty strong effect. If you have electrons contained in a bond, their repulsive forces are minimized slightly. So when you have unshared electrons in a particular molecule, they are going to push and take up more space than one would expect, and therefore cause these angles to shrink. Okay, so what you might expect to be 120, it would become less. Sorry about that. Less than 120. The other thing you can see is when you have a double bond, and now in a double bond you have more electrons, and they're going to need more space. And this also applies to a triple. So when you have a double or a triple bond, you have your electrons being shared in a smaller location, and they will also push with a bigger force, causing the remaining bond to become less as well. So we would expect this one to be 120, but it is really less than 120. Okay, so you need to be aware that two reasons that bond angles would be less than what we expect would be the lone pairs and the double bonds. So whenever you have lone pairs and double bonds or triple bonds in a molecule, you'll need to consider what the bond angle becomes. All right, in trigonal planar, you have a center atom with three things attached. And in a traditional trigonal planar, you have 120 degrees bond angle. When you become, if you are in a molecule where there is a double bond, as trigonal planar can be, this one would cause the bond angle to be less than the 120. Another effect you can see here in trigonal planar is in the fact when you have a bent molecule, because you have lone pairs. The lone pairs will also cause this to become less than 120. Okay, because both of these take up and have more repulsive power. They take up more space. They have more electrons that are pushing on the remaining bond with a bigger force, causing the remaining bonds to squeeze together. Here in tetrahedral, we typically have four things bonded to the center, and the bond angle is 109.5 when they're filled with four elements. Whenever you have a triangular pyramidal, meaning that you have replaced one of the bonds with a lone pair, your bond angle reduces, and it reduces to 107 degrees. If you go on then to bent in the electron domain of tetrahedral, the bond angle reduces even further, and it becomes 104.5. The numbers aren't necessarily as important as you understanding that the addition of the lone pair electrons caused the bond angle to be less than the original 109.5. In your triangular bipyramidal, you have two different bond angles depending on whether it's axial or equatorial. In the axial position, this is a 90-degree bond angle. In the equatorial position, this is a 120-degree bond angle. Now, if we were to work through the additional molecular geometries, adding lone pairs, your angle does change some depending on which one you have replaced. So here, the 90 is not affected, but the remaining bond angle, and this is going to be hard for me to show, the remaining bond angle here to here would also still be a little bit less than the 120. Okay. If you continue on into the T shape, you don't see a change because there is no effect on this 90. All right, and then the two lone pair sets are in the center on the equator, and they can't change the angle within the equator any further. The linear is not affected at all. It remains at 180. In octahedral, the bond angle effect is even more minimized because you started with all 90s, and if you remove one of the bond angle or the bonds to become square pyramidal, the overall angle just really, you don't see much of an effect. The bond angle here is 90 degrees. If you were to go on and then look at square pyramidal, there is absolutely zero effect by adding two lone pairs because they're equal and opposite. Equal and opposite meaning that the electrons on the top are going to repel with the same force as the electrons on the bottom, and so those remaining bonds stay right where they're supposed to be, and so the angle between is still 90, and you see no change. Here's a sample problem, and I'd like you to do three things for this particular molecule. I would like you to find the electron domain. I'd like you finding the molecular geometry and the bond angle for each central atom. And they are listed in red here. The central atoms are 1, this carbon here, well, I didn't mean to draw on it, this carbon here in the center, 2, this second carbon here, which includes these 3 attachments, and 3, this oxygen as the center. I'd like you to come up with the answers. So I want you to submit these to your homework, listing 1, 2, and 3, which will represent the 3 different center atoms, and then list the electron domain, the ED, the Mg, the molecular geometry, and the bond angle.